All right, let's dive into one of the most exciting, most mind-bending ideas in all of physics, going faster than light. I mean, it's the dream of every sci-fi fan, right? But what does real science have to say about it? Is it even possible? Let's get into it.
You know, when you look out at the universe, it feels boundless. But it's not. It has rules, and there's one rule, one cosmic speed limit that seems absolutely unbreakable. A barrier that holds everything in check.
And there's the number, nearly 300 million meters per second. We just call it c. And look, it's not just that it's, fast. It is the speed limit. It's the absolute, non-negotiable top speed for everything, for matter, for information, for cause and effect itself.
But what if there's a loophole? What if, hidden somewhere in the deep math that paints the picture of our universe, there's a little clue? A hint of some particle that doesn't just break the rule, but lives its whole life on the other side of it. Okay, so before we can even talk about breaking this speed limit, we've got to understand why it's there in the first place. What is it that makes the speed of light so special? And trust me, it's a lot weirder than you probably think.
And this is where things get really strange, because physics completely throws our everyday intuition out the window, right? Like, if you're on a train going 100 miles an hour and you throw a baseball forward at 20, somebody watching from the ground sees it going 120. Simple. Speeds add up. But light just doesn't care. It refuses to play along. It doesn't matter if you're standing still or blasting through space on the fastest rocket imaginable. If you shine a flashlight, you'll measure that light beam moving at the exact same speed, c. And this one bizarre, stubborn fact drove physicists crazy for years.
So the first big breakthrough came from a guy named James Clerk Maxwell back in the 1860s. He managed to unite all the equations for electricity and magnetism, and when he did, something amazing popped out. His math predicted this self-sustaining wave of energy that could just zip right through a vacuum. And the crazy part? When he calculated how fast this wave would go, using just a couple of fundamental constants, the number he got was, you guessed it, the speed of light. I mean, spot on. This was a huge deal. It meant c wasn't just some random speed we measured, it was baked right into the fundamental laws of the universe.
And then comes Albert Einstein. And he just flips the whole script. He looked at all this and said, "You're all thinking about this backwards." He realized the speed of light isn't just a speed limit for things moving in space. No, c is a fundamental property of space-time itself. Think of it like a cosmic conversion rate between space and time. It's the one constant speed that everything, and I mean everything, is always traveling at through this four-dimensional fabric of reality.
But here's where the plot thickens. Because inside Einstein's own elegant equations, the very ones that cemented c as this ultimate unbreakable law, there was a ghost, a strange little mathematical curiosity, a hypothetical particle whose entire existence depended on violating that very same law.
So let's take a quick look at this famous formula. Don't worry, it's not as scary as it looks. All it's really saying is that as your velocity v gets closer and closer to c, the speed of light, that bottom part of the fraction gets teeny tiny. And when you divide by a tiny number, the result gets huge, right? This means your mass starts to balloon, heading straight for infinity. To actually reach the speed of light, you'd need an infinite amount of energy. And well, that's just not going to happen. But physicists, they love to poke the bear. They love to ask, what if? So, what if we just break it? What if we plug in a velocity v that is faster than c? Well, mathematically, that little v squared over c squared bit suddenly becomes a number bigger than 1. And 1 minus a number bigger than 1 is a negative number. All of a sudden, you're trying to find the square root of a negative. And in your high school math class, that was impossible, right?
Well, for a long time, yeah, it was impossible. But then mathematicians came up with this whole new toolkit called complex numbers, and the star of the show is the imaginary number I. Now let's be super clear here. The name imaginary is really unfortunate, because these numbers are anything but. They are absolutely essential for describing very real-world physics, like AC circuits and the entire weird world of quantum mechanics. So what this equation was telling us is that a faster-than-light particle wouldn't have an impossible mass, it would have an imaginary mass. And this wild idea got a name, the tachyon.
So, okay, let's just run with it for a second. If we say these things could exist, what would that universe even look like? Well, get ready, because it would be a place where the basic rules of logic, the stuff we take for granted, just completely fall apart. The number one problem, the big one, is causality. That super simple idea that cause comes before effect. You flip the switch, then the light comes on. But because tachyons can outrun light, for some people watching, they would seem to be traveling backwards in time. And that creates instant paradoxes. I mean, you could literally build a device, send a message, and get a reply to that message before you'd even finish typing it. The whole universe would just become this nonsensical, tangled mess.
And if you thought that was weird, the physics of these things is pure bizarro world. Everything is backwards. For you and me, if we want to speed up, we need to add energy. Makes sense. But for a tachyon, you'd add energy to slow it down. As it gets closer to the speed of light, but from the fast side, its energy would shoot up to infinity. So to go even faster, a tachyon would have to lose energy. It's wild. It means the speed of light is like this two-way wall. We're trapped on the slow side, and they would be trapped forever on the fast side.
So yeah, because of all these paradoxes, you won't find many physicists who think tachyons are real, actual particles whizzing around out there. But, and this is a huge but, that does not mean the idea is useless. Far from it. In modern physics, when a tachyon shows up in your math, it means something incredibly important is happening.
Here's the modern take on it, the big shift in thinking. Today, a tachyon isn't seen as a particle at all. It's like a warning light on your car's dashboard. It's an error message popping up from the universe's code telling you, hey, this thing you're describing, it's unstable. It's about to fall apart and change into something else.
So let's really dig into what that warning light is saying. In the language of quantum field theory, having an imaginary mass is the same as having a negative mass squared. So instead of thinking, oh, a faster-than-light particle, physicists now think, this field is in a really unstable state. It's like a ball balanced perfectly on the very peak of a hill. It can't stay there, right? It's got way too much energy. That tachyon is the math screaming at you that the ball is about to roll down into the valley, into a much more stable, lower energy state.
And believe me, this isn't just some abstract idea. This exact thinking led to one of the most important discoveries in modern physics. When physicists were first working out the theory of the Higgs field, guess what popped up in their equations? A tachyon. That was the warning light. That was the big clue that told them the Higgs field in its initial state was unstable, like that ball on the hill. It needed to roll down into a stable state, and in doing so, it would fill all of space and give other particles their mass. The tachyon itself wasn't real, but the instability it pointed to, that was the key to the whole Higgs mechanism.
So this is where we end up, with this kind of beautiful dual identity for the tachyon. On the one hand, yeah, it's this crazy logic-breaking particle from our science fiction dreams, but on the other hand, it's become this incredibly powerful tool that helps physicists probe the stability of the universe itself.
So let's wrap this up. What are the big takeaways here? First, that cosmic speed limit c isn't just some arbitrary rule. It's woven into the very geometry of spacetime and causality. Second, yeah, tachyons are a thing that can exist in the math, but if they were real particles, our universe would make no sense. And maybe most importantly, in modern physics, finding a tachyon in your theory is actually a good thing. It's a signpost, a big flashing arrow pointing you towards a deeper discovery, just like it did for the Higgs.
Which leaves us with one final, fascinating question to chew on. Is the tachyon just a ghost in the machine, a useful mathematical fiction that helps us find other, real truths? Or could it be something more? A little crack in the door, hinting at a whole other layer of reality, one with totally different rules that we just don't have the tools to understand yet. What do you think? The answer is still out there.
Health is the most precious gift. If this video helped you or someone you love, please like, subscribe, and share so more families can stay safe and healthy.